everyone. Imagine if your camera could not only capture memories, but actually take you on a virtual tour of a scene from every angle, like having eyes in the back of your head. Today, we're diving into the fascinating world of Odin, a model that transforms a single image into a 3D adventure. From cathedral ceilings to bustling kitchens, it's not just imaging, it's imagining. Let's explore how 1,360-degree videos unlock new dimensions of creativity.
Let's start by examining the core challenge this research addresses. In computer vision, a crucial goal is to help machines understand the three-dimensional structure of real-world scenes. Synthetic datasets can provide endless views of virtual objects, but real-world 3D data is much rarer and harder to learn from. Videos might seem like a solution, yet typical videos only capture a scene from limited viewpoints, which constrains 3D understanding. That's where 360 videos come in. They record entire environments from all angles, providing diverse, corresponding views of objects from multiple perspectives. The authors introduce the 360:1M dataset, consisting of 1,360 videos, and show how to find frame correspondences efficiently. Training on this large-scale real-world dataset, they present Odin, a diffusion-based model capable of generating new viewpoints of a scene from just a single input image. With Odin, you can move a virtual camera, translate, rotate, or zoom, while maintaining geometric consistency. Odin surpasses existing methods on benchmarks for novel view synthesis and 3D reconstruction, all without extra fine-tuning. To appreciate why this matters, consider how humans navigate and interact with the world. Our ability to understand 3D structure guides us effortlessly. Replicating this understanding in machines has been a long-standing goal in fields like robotics, computer vision, and graphics. Synthetic 3D models helped researchers initially, but translating these successes to real-world scenes remains difficult. Videos theoretically contain 3D cues embedded in the changing viewpoints as the camera moves. However, extracting consistent 3D information from ordinary video footage has proven challenging. Many efforts have been made, but progress has been slow. The heart of the problem lies in leveraging readily available, large-scale visual data, like everyday videos, to build stable 3D representations. This paper's approach, using 360 videos, is an attempt to crack that problem at scale. So how does the model achieve this? Odin starts with a single input image of a scene, and then predicts new, realistic, 3D- consistent views. Imagine taking a photo of a building, and then, using Odin, virtually stepping to the left, moving closer, or rotating the camera angle. Odin generates what the scene would look like, preserving geometric and structural consistency. Its training on a massive, diverse dataset of real-world 360 videos gives it the ability to handle complex, varied scenes, which more controlled datasets and models struggle with. A key advantage is that Odin doesn't just guess what's around the corner. It infers the underlying 3D structure and layout of the scene. Existing 3D models often fail at maintaining consistent geometry when generating multiple views. In contrast, Odin synthesizes smooth, natural transitions between viewpoints, leading to more coherent visual results. But why rely on 360 videos in the first place? Standard videos are limited to the camera's forward-facing view, making it hard to find multiple overlapping angles of the same object. The camera's narrow field of view means objects often don't reappear from different positions. Moreover, searching for matching frames within large video collections is computationally overwhelming. By starting with 360 videos from YouTube, 1 million of them, the authors can sample different angles of the same scene without relying on fortuitous camera motion. Odin then uses these diverse viewpoints to learn how objects and environments look from all directions. The result is a model that excels at novel view synthesis and 3D reconstruction. Tests on datasets like DTU and MIP NeRF 360 show Odin outperforms other methods without any scene-specific tuning. This demonstrates a step toward more generalizable, real-world 3D modeling. Before exploring the detailed methods, let's consider related work. Traditional novel view synthesis techniques, like NeRF, assume you have many images of the same scene with known camera poses. While these methods have shown impressive results under controlled conditions, They often break down in realistic, unconstrained environments. Diffusion-based generative models emerged as a promising alternative. Prior works, such as 0NVS, attempted to generate full 360 views from a single image, addressing problems like depth-scale ambiguity. Other strategies integrated point clouds or forward warping. Yet, these earlier methods struggled with complex, real-world conditions and broad camera movements. Additionally, camera pose estimation methods, like those using kernel map or SLAM, help align views by inferring camera positions from images. The paper's approach leverages ideas from these methods, but on an unprecedented scale, and with a more diverse training set, which helps overcome prior limitations. Scaling multi-view datasets has historically been difficult. Controlled datasets like MV ImageNet or MIP-NeRF 360 provide many images but often lack variety. Others, like Objaverse or Google Scanned Objects, specialize in either specific object categories or controlled tasks, limiting their relevance for broad real-world scenes. The author's solution leverages the diversity of 360 YouTube videos. By tapping into this massive, diverse source, they build a large-scale dataset capturing scenes in all their complexity. The big challenge is establishing accurate correspondences and estimating camera poses at scale. This step is critical for turning raw footage into a resource that fuels learning for Odin and moves beyond the constraints of previously curated datasets. Now, let's consider how 360 videos compare to standard videos. Traditional cameras only face one direction, providing a narrow glimpse of a scene along a limited path. Finding frame correspondences is challenging because we often need different angles of the same object, which standard videos rarely provide. In contrast, a 360 camera records the entire surrounding environment. As it moves, it captures every direction at once. This makes it straightforward to select frames that show the same object from multiple viewpoints. Instead of guessing whether another frame might reveal a different angle, 360 data ensures that such viewpoints exist within the same video, enabling more efficient alignment and multi-view matching. To convert 360 videos into a usable dataset, the paper outlines a systematic process. First, they sample frames at 1-second intervals. Each panoramic frame is then split into 4 90-degree slices via equirectangular projection, making it easier to compare different parts of the frame. To find matching frames, the system considers a 20-frame window and uses a model called DUST3R to estimate relative camera poses. If the model is confident about the pose, those frames are considered correspondences. To refine these matches, gradient descent fine-tunes the pitch and yaw so that overlapping regions align even more closely. Finally, pairs with too little camera movement, less than 0.25 meters, are discarded because they offer limited new information about the scene. Computational efficiency is a big concern. Checking every possible frame pair would be too expensive. To tackle this, they start with short-range matching in a limited time window, and then build a graph of correspondences. By identifying connections through shared intermediate frames, long-range matches can be inferred without exhaustive searches. Another complexity is scale ambiguity. Structure from motion tools like DUST3R provide relative poses, but there's no inherent scale. To fix this, the authors integrate an external depth estimator. By merging relative poses with depth estimates, they align everything to a consistent global scale, ensuring that the 3D structure makes sense in real-world terms. Armed with an efficient matching strategy, the authors constructed the 360:1M datasets. Starting from 1,076,592 equirectangular format YouTube videos, they applied filters to remove duplicates and low-quality samples. After processing, they ended up with a dataset of over 80 million unique frames, about 75 frames per video on average. These frames span 15 categories, including travel and events, and pets and animals. In total, they identified around 363 million frame correspondences with relative poses. This unprecedented scale and diversity sets the stage for training models like Odin to learn robust, generalizable 3D representations. With the dataset in hand, The next step is to compare various methods for novel view synthesis. Figure 3 in the paper, not shown here but described, compares Odin with other methods like 0-1-3 and 0-NVS. Odin's outputs maintain geometric coherence even for unseen parts of a scene. Furniture details in a kitchen or the layout of outdoor spaces come out more accurately. The key idea here is to generate a series of images along a camera path, conditioned on just one source image. Traditional NVS methods rely on multiple images of the same scene, but Odin's diffusion-based approach, trained on large-scale data, allows it to work from a single view while still capturing real-world complexity. The model's core techniques revolve around viewpoint condition diffusion and motion masking. In viewpoint condition diffusion, the model takes in an input image and specified camera movements, rotations, and translations, and generates the corresponding new view. A latent diffusion model is trained to understand how scenes look from a wide range of angles. The second technique, motion masking, addresses dynamic elements in scenes. Real-world videos aren't always static objects, and people move. Motion masking uses a learned mask to ignore these moving parts, guiding the model to focus on consistent aspects of the environment. By including a mask channel in the U-Net denoiser, Odin becomes more robust to unpredictable changes, ensuring that the generated views remain stable even when objects move. Odin can synthesize entire 3D environments from a single input image, enabling virtual camera navigation. The paper illustrates this with complex scenes, like a cathedral. From one image, Odin generates views along a trajectory that reveals architectural details not visible in the original frame, such as the lofty ceilings and the length of the hallways. By relying on learned priors from the massive 360 dataset, Odin achieves a remarkable level of geometric and visual consistency across these synthesized views. This section further refines the idea of handling dynamic elements. By introducing a mask that selectively ignores uncertain areas, the model avoids collapsing into trivial solutions where it discards too much information. An auxiliary loss encourages the mask to keep meaningful, static parts of the scene, striking a balance between noise removal and content preservation. For 3D reconstruction, Odin does not simply produce one-off images. It generates a sequence of frames along a chosen camera path. Each frame is consistent with the others. After generating them, a tool like Dust3R can integrate these frames into a coherent 3D model. This ensures not only visual realism, but also accurate geometry, making the outputs useful for various downstream applications. Next, the paper evaluates Odin on standard benchmarks like DTU and MIP-NeRF 360. DTU involves smaller, simpler objects on a tabletop, while MIP-NeRF 360 covers more complex outdoor scenes and building exteriors. The authors measure performance using metrics like PSNR, LPIPS, and SSIM, which reflect image quality and perceptual similarity. They also test Odin on their new 360:1M dataset. For 3D reconstruction, they compare Odin with methods like 0-1-3 and MCC. Using Dust3R to reconstruct from generated frames, the evaluation employs chamfer distance and volumetric IOU, also known as intersection over union, to quantify how close the reconstructed geometry is to a reference standard. Odin's results show it handles both novel view synthesis and 3D reconstruction effectively. The quantitative results indicate that Odin generally outperforms comparable methods. On DTU, the improvements might be smaller due to the simplicity of the scenes. But on MIP-NeRF 360's more complex conditions, Odin pulls ahead significantly. For instance, Odin's LPIPS and PSNR metrics are better than those of 0-NVS and 0-1-3. When it comes to reconstructing full 3D scenes, Odin consistently produces geometry that aligns closely with pseudo-ground truth reconstructions. While some methods can produce plausible single views, they struggle to maintain consistency across multiple angles. Odin's training on diverse and extensive real-world data enables more stable and coherent scene modeling. Further 3D reconstruction comparisons, shown in Table 3 of the paper, confirm Odin's strengths. Against methods like MCC and SJCI, Odin shows improvements in chamfer distance and IOU, indicating more accurate and complete geometric understanding. While Odin filters out dynamic elements, it doesn't yet model them explicitly. Extending these techniques to handle changing scenes, or 4D representations, is a possible future direction. On the broader impact side, Odin's capabilities could be useful in areas like augmented reality, virtual reality, and robotics, but they also raise concerns about misuse, like generating deceptive images. The authors call for careful consideration as this technology evolves. In conclusion, the paper presents Odin. Trained on the largest 360 video dataset collected so far, Odin overcomes long-standing limitations in novel view synthesis and 3D reconstruction by learning from extensive real-world data. It synthesizes realistic, 3D consistent views from just one input image and performs well across established benchmarks. Looking forward, the authors suggest exploring dynamic scene modeling, or 4D, as a next step. They also plan to release the code, models, and dataset publicly, inviting further research and enabling new applications that benefit from more advanced 3D scene understanding. And that's a wrap on this deep dive. From geometric consistency to dynamic masking, Odin paves the way for an exciting future in 3D scene understanding. Let's see where this innovation leads next.